Introduction. The one-dimensional approximation. An open channel always has two sides and a bottom. Two sides, bottom. Where the flow satisfies the no slip condition. Therefore, even a straight channel has a three-dimensional velocity distribution. Three-dimensional. Some measurements of straight channel velocity contours are shown in this picture here. The profiles are quite complex, with the maximum velocity typically occurring in the mid-plane about 20% below the surface. In very broad, shallow channels, the maximum velocity is near the surface and the velocity profile is nearly logarithmic from the bottom to the free surface. In non-circular channels, there are also secondary motions similar to the closed-dog flows. If the channel curves or mean rest, the secondary motion intensifies due to the centrifugal effect, with high velocity occurring near the outer radius of the bend. Curved channels, natural channels, are subject to strong bottom erosion and deposition effects. With the advent of supercomputers, it is possible to make numerical simulation of complex flow patterns, such as shown in this picture for the streamlines. However, the practical engineering approach used here is to make a one-dimensional flow approximation. Flow approximation as shown in this picture. Since the liquid density is nearly constant, one-dimensional flow approximation. The liquid density is nearly constant. The steady flow continuity equation reduced to the constant volume flow line the channel, which is the continuity equation is the volume, a constant volume flow is the relation of equals to constant. Let me write again. Continuity as volume flow AX Bx constant, where V is average velocity and A is the local cross-sectional area. A second one-dimensional relation between velocity and channel geometry is the energy equation. Including friction losses, if point 1 upstream and point 2 downstream, are on the free surface where P1, P atmosphere, and we have the steady flow, so we can write this relation for energy equations with the same pressure in 2 points but different maybe elevation from our assumed datum. Where Z denotes the total elevation of the free surface. Which includes the water depth, H, plus the height of the bottom sloping for example sloping bottom This is for a steady flow. The friction head can be calculated as this relation, the friction coefficient from the diagrams or tables, hydraulic diameters, the average velocity, where F is the average friction factor, as we said in chapter 6, some relation for this factor between section 1 and section 2 in this problem. Cis channel are irregular in shape. The size is taken to be the hydraulic radius as this relation RH the local Reynolds number of the channel would be the kinematic viscosity, which is usually highly turbulent for the only commonly occurring laminar channel flow are the thin sheet that forms a rainwater drains from the Crowned Street and airport runways. The weighted perimeter P, as also shown in this picture, includes the side and the bottom of the channel, but not for the free surface, and of course not the parts of the side above the water as shown here. Bottom and side, which have contact with fluid, this water for example. For example, in this channel we have, in this example, the weighted shown, perimeter weighted shown with P, and P equals to, for a rectangular channel. Although the Moody chart would give a good estimate of friction factor in the channel flow in chapter 6, in practice it is a seldom used. An alternative correlation due to the aerobic manning discussed in the next section is the formula of choose in open channel hydraulics.